All right, let's jump right into this explainer. Now, in explainers 8 and 9, we already laid out exactly why packets of data might slow down on their journey. But today, we're going to tackle a much more frustrating question. What happens if the packet never arrives at all? Or what if the surviving data is squeezed down to an agonizing crawl?
Look, we've all been there, right? You're on a crucial call and boom, completely frozen face. Or you're trying to download a file and it says it's going to take 3 hours instead of 3 minutes. We usually just throw our hands up and blame bad internet. But today, we're actually diagnosing the exact, distinct technical causes behind these two very different network failures.
To do that, let's quickly bridge back to this 4-stage delay pipeline we mapped out previously. Every single packet has to pass through these stages. But to understand today's failures, we really need to zoom in on stage 2 right there, queuing. This is the totally unpredictable waiting room at the router, and as you're about to see, this is exactly where packets meet their demise.
Okay, here's our game plan for today. We'll cover the mechanics of packet loss, throughput, and bottlenecks, internet-scale links, comparing loss versus throughput, and finally, real-world diagnostics.
Section 1. The mechanics of packet loss, finite buffers, and dropped data. Let's get into it.
So to really grasp packet loss, you kind of have to picture the router's architecture. Think of a router exactly like a bank teller with a limited waiting line. If packets arrive faster than the router can actually transmit them, a queue forms. But here's the catch. That queue relies on the router's memory buffer, and that memory is strictly finite. If a sudden burst of data hits, let's say 5 massive packets all slam into a router with only a 15 megabit per second link at the same time, the buffer just runs out of space. When the next packet arrives and finds a full house, the network literally just drops it. It bounces off into absolute oblivion. And the exact moment that happens is governed by this traffic intensity formula right here. Let's break down these units real quick. L is the packet length in bits, and A is the average arrival rate of packets per second. You multiply those, you get your total arrival rate of bits. R is a router's transmission rate in bits per second. So when the arrival rate meets or exceeds that transmission rate, meaning L times A divided by R is greater than or equal to 1, that queue is going to grow endlessly. And since buffer space is finite, under those conditions, packet loss isn't just possible, it's mathematically guaranteed.
What's really fascinating is how the internet copes with this mathematical inevitability. It totally depends on the protocol layer you're using. So, TCP? It's basically a perfectionist. When TCP sees a dropped packet, it reliably retransmits the lost data, but it drastically slows down your entire connection to clear the congestion. UDP, on the other hand, which we use for live voice and video, values speed above all else. It literally just ignores the loss and plows right ahead. It uses forward error correction, which is this clever math that rapidly guesses the missing pieces, meaning it can tolerate like 10 to 20% loss before your video call turns into a garbled mess.
Moving right along to Section 2, throughput and bottlenecks, the flow of digital fluid.
So now we know why data disappears entirely. But what about the surviving data? Why does it sometimes move so incredibly slowly? Well, it's absolutely crucial that we separate the concept of raw link bandwidth from instantaneous throughput. Your ISP might sell you a 100 megabit connection, sure, but your end-to-end throughput is the actual real-world rate of bits successfully landing on your device from a specific server at any given instant.
Before I hit you with the formula for this, think about plumbing for a second. Imagine a water system where a massive, wide pipe connects to a tiny little straw right before your faucet. What dictates the final flow of your water? The massive pipe's capacity doesn't matter one bit, right? The flow is entirely restricted by the straw.
And the answer is mathematically expressed right here as the minimum of the server's rate, R sub S, and the client's rate, R sub C. This means your entire digital pipeline is literally only as fast as its narrowest bottleneck. Even if you've got a blazing fast gigabit connection at your house, if the server you're downloading from is stuck on a slow uplink, well, your throughput is going to match that slow link.
Let's run the numbers on a quick example to make this concrete. Say you're downloading a 64 million bit file. The server is pushing data out at 2 megabits per second, but you have a nice 10 megabit per second connection at home. Your bottleneck is that 2 megabit server. So, applying our formula, 64 million bits divided by a bottleneck throughput of 2 million bits per second means it's going to take exactly 32 seconds to receive that file. Your 10 megabit connection couldn't speed that up at all.
All right, Section 3, Internet Scale Links.
how this all works when sharing the network core.
Up until now, we've really only looked at the very edges of the network, your house and the server. But zooming out, the core of the internet relies on these massive, highly over-provisioned links. The thing is, they're shared. If thousands of users suddenly hit a single core link at once, that pipe has to divide its transmission capacity equally among everyone. So our formula actually updates to the minimum of the server rate, the client rate, or the core link rate R divided by N, which is the number of simultaneous users.
Now usually, the bottleneck is at the edge. But what happens when the core gets overwhelmed? Say 10 clients are downloading from 10 servers through a shared 5 megabit per second core link. That massive pipe gets divided by 10. All of a sudden, you've created a miserable 500 kilobit per second bottleneck right in the dead center of the internet, completely choking off everyone's otherwise fast connections.
Let's head into Section 4, Loss versus Throughput Compared, our quick confusion buster.
People mix these two up all the time, but look how clearly we can separate a dropped packet from a slow packet here. Packet loss is fundamentally a memory issue. A router runs out of buffer space, forcing protocols like TCP to panic and retransmit. Throughput, however, is a speed issue, a physical bottleneck restricting the flow rate of bits. We measure loss as a failure percentage, but we measure throughput as an active speed in bits per second.
Which brings us to our final section, real-world diagnostics. Let's solve our hook.
Let's tie this all back to those frustrating symptoms from the very beginning. That frozen face on your Zoom call, it's not just generic bad internet. It's specifically a router overflowing its queue buffer. And because Zoom uses UDP, those lost packets aren't retransmitted, leaving your software completely hanging, unable to draw the next frame of your coworker's face. On the flip side, that painfully slow file download is just a pure throughput bottleneck. Your data stream is getting squeezed by a narrow access link, probably at the server's end.
And, stepping back, this just brilliantly highlights the sheer chaos of our networks. We are relying on an infrastructure filled with finite buffers that constantly drop our data and narrow pipes that relentlessly throttle our speed. So it leaves us with this final provocative question. If the physical network is this volatile, how does the internet ever actually feel reliable to us? What ingenious layers of software are secretly hiding all this chaos from our screens? Well, that is exactly what we're going to uncover in Explainer 11 when we tackle the absolute magic of protocol layering. See you then.